Hello, my name is Jordan Stevens, and this is my simulation project. This document is going over simulation study of Dreyer Urgent Care Facility. The problem is that the Healthcare Service Center is considering modification of the current doctor schedule, this doctor schedule right here, and it should decrease the average time the patients spend in the facility, so like waiting lines and the time that the patient spends in the system, TIS. So their proposed solution is a new schedule, which on average will add an extra doctor, like where it shows right here. The average for the current MDs on schedule, doctors on schedule, is 2, and the new proposed one is going to be 3, or an average of 3 doctors. And basically they're just trying to prove that based on the model of the system. Now they go on into the introduction into where they show like Dreyer, where it is, how they got their data, and how their data could be skewed because Dreyer Urgent Care Centers never had a time analysis. They've never had an analysis of actually their own facility. So they actually used a similar facility from 1995, so there might be skewed analysis here. And basically what they're trying to say in this is that they're trying to decrease the average time in system and decrease the utilization of each resource. They then go on to say the importance of modeling and simulation and the program that they use, Arena. And then they go into the introduction of how the model is. It works from 7 a.m. till 9 p.m. each day. And they have 4 patients that show up. They have critical patients, appointment patients, walk-in patients that are eligible for fast track, and just regular walk-in patients. Now, each one of these has a priority value with them too. Like critical patients are priority number 1, appointment patients priority number 2, walk-in patients priority number 3, walk-in patients with fast track are priority number 3, and regular walk-in patients are priority number 4. After their description of the arrivals, and they then go on to say some assumptions that they have. Some assumptions is that there's an infinite capacity for any of the stations that do not have a doctor in them. And they're saying here that they have 2 stations with doctors in them, and that just to keep the capacity the same in both the stations. And then they go in more into like how their data collection is, and they got it from Dreyer's historical data from a 1995 facility, very similar, but it actually wasn't from there, so it's old. Then they go into the patient's arrival, which they show that the patients arrive in a log normal distribution, but they never give the actual distribution time or their arrival rate for the patient's arrivals. Then they show you the patient flow diagram, in which the patients arrive at registration desks. Then they go through a sorting facility, in which they're determined if they're a critical patient, an appointment, they're a patient with appointment, a fast track patient, or just a regular patient, and they're assigned priorities with that. Once they're done with that, they go to the initial assessment, and then they wait on the actual doctor, and then they go to the doctor, and they're examined by the doctor. Once they're examined by the doctor, then they go into another probability in which they're either assigned by the doctor to have a lab test, have an X-ray, have both, or have none. And if they have a lab or X-ray, they return to the doctor for a final assessment. They then go into like the actual percentages, like 7% of all patients are the priority number 1 critical patients, and so on and so forth. Then they also go into the percentages of how many go into the X-ray, how many go into the lab, how many of both. After that, they give the service times for all the stations that are in this document. So they have patient registration, nurse, primary screening, the doctor examination, lab test, an X-ray room, and the post-testing. Okay, and based on this model, I built my facility where patients arrive, they go to critical condition, which this is just a probability, like basically just a sorting center, because it has processing time of 0, so it doesn't affect the system at all. And they also have connectors which don't affect the system at all, which don't add to the time in system. So they start off with is the patient critical condition? Yes, 7%, and no, 93%. And then they go on to registration. A patient, if they're in critical condition, doesn't have to go through registration, so that's why it's before. And then they go into registration. Registration is 3.45 minutes. And then after that, what happens in this part right here, this part where the appointment, all these part right here, the model assessment, fast track appointment, they are what happens at the actual registration. So they all have a processing time of 0, so they don't actually affect the system. It's just a way that I use to sort and prioritize the patients into the 4 categories. So they have appointment. Is appointment? Does the patient have appointment? Yes, no. And these values right here are determined by simple algebraic cross product, because of just the percentages from here. Because 93%. Okay, and then it goes through this, and then it goes to model assignment, triaged. What all these do is these servers are just here to assign a priority value. So they have on entering, they have a set priority value that they give of 1. Once they set a priority value, it goes 1, 2, 3, 4. So they all set a priority value. And then from then on, at all the other stations, they have a ranking rule of smallest value first. So the critical patients are priority number 1, so with all these next stations. After they go to the sorting system, the first sorting system, they go to initial assessment, which has a random exponential of 3.4 minutes. Then they go to examine, which has a random exponential of 15.9 minutes. And then they go to another sorting system, which is what does patient require? A lab test, x-ray. They don't need neither, or they need both. And these are all given by the connectors too. And they have their own distribution times too. Okay? So what this actual study is showing, though, is they have a current schedule for the doctors, and they have a proposed schedule for the doctors. So they have what I did for the schedule, to make a schedule like the one given in the paper right here, is that I made a work schedule in Simio. To make a work schedule, I went to data, I went to schedule, and then I went to date patterns. Now the first day pattern is the current day pattern, so an average of 2 doctors around that, and they have for each hour they have a certain amount of doctors working, like in the table given. And then I gave the proposed schedule, which has an average of 3 doctors working. Now once these are given, I gave a work schedule with 7 days a week. Every day has the same schedule. And then I went back to the facility, and I went to work schedule, and the capacity is number of workers, and I put it as current. Okay? And I put it for both of these because doctors work both the examined and the returns to MD. And once I did that, I went to experiment, and I actually had to guess the initial value, the arrival rate, to equal 64%. So basically, in the model, they don't give me an actual arrival rate. I actually had to guess that myself. So basically, I did everything in the system right, exactly what the paper said to do, including the schedule, and then I guessed around for values of the minutes, and I came up with 22 minutes as my initial rate that matched the current schedule with the scheduled utilization results. So basically, in the paper, it says that at the current schedule, there's a 64% utilization for the doctor. Okay. So in my Simio model, I went to my experiment, went to my pivot grid, and I have scheduled utilizations here. So examine and register and returns to doctor. Those are both doctor scheduled utilizations. So I add these two together, 54 plus 10, that's 64%. So that's exactly where the other one is, okay? Now once this happened, I go back to my model and I change to the proposed schedule, just like in the document. And then I go to my experiment, and then I run my experiment. While I'm running my experiment, I'm going to go over the results. So they have our results here. Their results, they ran it through Arena, and they have the way their model was set up. And they also have a 95% confidence interval, okay? Now their study shows that there was an 18% reduction in the average time in system from 44 minutes to 36 minutes, okay? And then they also show like how they went into normal distribution when I went into exponential distribution. They then show the differences between the current schedule and proposed schedule. See how the utilization drops here by 13% for the doctor, which is what they want, because the doctor is the bottleneck of the system, which would decrease the average time of system. And then they go on to say, hey, if one bottleneck is decreased to a point where it's negligible, wouldn't another bottleneck arise? And if another bottleneck arises, would they have the necessary materials? And most of the time they would not if it's another station. So they actually show down here the average number of doctors, like here, where they have a certain number of doctors, and they notice that if they have an average of 6 doctors, the actual scheduled utilization, the bottleneck switches to the exam room. So because of that, they know that their bottleneck right here does not switch because it's under average of 6 doctors per minute. So they showed that their system is they show that their system actually decreases the average time of system while also decreasing the utilization, which is what they want to solve the problem. Now in my simulation, I got 42% for the scheduled utilization for examined, and I got 7% for my scheduled utilization for returns to MD. Now that's 49% scheduled utilization for my proposed schedule, which is just 2% off of theirs. So I have a 15% drop in mine. And also, if you notice, my average time of system is a lot larger than their proposed time of system for 44 minutes and 36.1 minutes. This is because of my distribution times, and also I was not given a arrival rate. These are major things that would lead me to have a very different result than theirs. But even though I had a very different result than theirs, mine also showed that there was a drop. There was a drop in percentage of the scheduled utilization, and there was a drop in the average time of system, which would further prove that their solution is correct. They then go on to say like how this does not change the bottleneck. It's the same bottleneck. It reduces the time by 18% and it reduces the scheduled utilization. And that is it.